Okay. Hello everyone. This is Dr. Barham. Yes, it's me again. I actually, instead of starting 3.8, I wanted to go back over 3.7, the chain rule. There are a couple things that I didn't mention that I want to mention, just another way to look at it. And in your book, it has it a certain way for the homework problems, and I want to make sure you know how to approach it. So what we did in class, because in class, I really just wanted to do a lot of examples, and which is what we did. But I want to just kind of pinpoint some other things that you should know as well in terms of the chain rule. And so, excuse me, 3.8 I'll save for Wednesday. So your exam will be from 3.1 to 3.8. And you should definitely read 3.8, the derivatives of inverse functions, because we'll cover that. And possibly 3.9. So let me change that. Possibly 3.9 is just exponential all functions, the derivatives. So we'll see. I'll let you know on Monday. But as far as reviewing for the exam, for now, definitely sections 3.1 up to 3.7. Definitely make sure you go over and go through and review. And if you do that first, and then, so if whatever I put from section 3.8 or 3.9, it won't be something that'll be too involved that you have to hurry up and remember it in a couple of days. It'll sort of be an extension of what you've already done. Okay. So because I'm going back over 3.7, so I'm hoping to finish this, if not in this video, by the next video, because there are just a few things that I want to touch upon that I didn't get a chance to do in class. So it might go over into the second video if I don't, because I kind of want to stop between 10 to 15 minutes. But I will be posting, or depending upon when you've listened to this, I posted your WebAssign problems, and there are a lot to do, so I don't want to give you any extra work. So there's no other assignment that you need to turn in. You don't have to turn in anything to me in class on Wednesday, but Wednesday on WebAssign, I'm giving you actually homework from 4 sections: 3.4, 3.5, 3.6, and 3.7. So that's a lot of sections. 3.7 is the bulk of your problems, but in 3.5 as well. So it's just a really good practice. 3.4 to 3.7, that's a really good practice for the exam. And then, of course, you need to look back over 3.1 to 3.3, and then 3.8 if I give you that, or 3.9, depending upon what I give you for on the exam. Okay. So, and it's due Wednesday. So that's why I didn't want to give you any extra work, because I really want you to focus in on these homework problems. So if you wait until Wednesday morning, even to do these homework problems, you've waited too late. And honestly, you need to start this weekend. Okay. Just do some problems at a time. Don't wait to the last minute, because that's going to frustrate you. You're going to rush through it, and you really need to understand to be successful. And I want you all to be successful. Remember, I only dropped one exam. So if you didn't do well on that first exam, then the second exam, you need to do better than whatever you did on that last exam. And you want to strive for really, doing really well if you didn't do well on that first exam. Okay. All right. So on to chain rule. So chain rule, again, like I said in class today, it's used to differentiate composite function or composition, right? Okay. And so I just wanted to quickly, because I know some of you may not have remembered what a composite function was, just to put it back in your memory. Let's say we have a function f of x equals x squared, and g of x is the square root of x plus 1. Then the composite of f and g, denoted f and that circle g, is defined by f of g of x, and that's f of g of x. And this is not, keep in mind, that's not necessarily the same. And in most cases, it won't be, unless it's in their inverse functions, right? So these are not the same. If they're the same and they're equal x, then they're inverses of each other. Remember that about inverses? Hopefully, yes. Maybe not, but if you don't, you will now. Okay. All right. Okay, so here's the formal theorem for chain rule. So I didn't make sure you write this down because I didn't give it to you formally in class. If f and g are differentiable functions, then f of g of x, or f composed with g, is differentiable, and f of g of x, that derivative. So remember, This notation right here means derivative, equals, and what I was talking about in class, you start with the outer function, so f prime of g of x, leave that inner function alone, times g prime of x. Okay, sorry. Okay, so here's what I didn't mention in class, and it's sort of an important note. I think I did something along sort of similar, but not exactly, but I think your book talks about it this way. Just another way to look at chain rule, especially this is useful if you have sort of nested functions nested within each other sometimes. I think so. We'll look at an example. So it is often useful to write the composite function as f of u, where u equals g of x. So sort of use this substitution. So if we keep that in mind, then in this manner, hopefully you can see that, f of u, that derivative, equals f prime of u times u prime. Okay, and I hope you guys can read that. So that's f of u, that derivative, equals f prime of u times u prime. Okay. Okay, so let's look at this example. Well, let y equal cosine of x cubed, and we want to find y prime. Okay, so using that method that I just talked about, we can let u equal x cubed and f of u equals cosine u. Okay, so looking, if you go back to the last slide, looking, the outside function was our cosine, and then the inside function is our x cubed. So looking at the substitution that we use, f of u would just equal cosine u, and u would equal x cubed. Okay, and so what we do, so I think I did something similar to this in class, is that u prime equals 3x squared, right? Just the power rule, and f prime of u equals negative sine u. Okay. All right. And thus, by the chain rule, okay, so we have f of u prime equals f prime of u times u prime. This is really just a way to look at it more simplified, because sometimes I know it can be complicated if you keep all the variables the same. So this is really just sort of a substitution type of method to make it look a little simpler. It's still the same, you get the same answer. Okay, and so this equals, well, f prime of u is negative sine u, and u is x cubed, right? So you can either write negative sine u times 3x squared, and then just remember your final answer should have x. If you start with x, or if you start with t, with that, whatever variable you start with, your final line should have that variable. So we just need to go back, we let u equal that. So it's just a form of substitution. It's another way, and your book talks about this, so I wanted to make sure I mentioned that. Okay, and of course if you want it, we usually bring that coefficient front, so we can rewrite this as negative 3x squared times sine x cubed. Sine of x cubed, make sure it's in that function. Okay, so let's look at this example, and using that, we can sort of call it the u method for chain rule, using u, f of u and u for our chain rule. All right, so we need to calculate dy dx. Remember, and I should make a note here that is called differentials. Okay, dy with respect to dx. That's another way to talk about the derivatives. We have our y prime. So remember the different forms. You definitely need to know various definitions that we always talk about for the exam. So that's just a hint for those listening to this video. Okay. All right. So we're going to calculate this for y equals tangent of x over x plus 1. Okay. So let me now want to change colors. Okay. So we're going to let we can start with our f of u, where f of u will equal what? Well, our outside function is tangent u. And u is x over x plus 1, okay? Then we need to calculate our derivatives. So f prime of u equals, and I just want to put it in different colors, so there's nothing wrong with it. I just want to, f prime of u equal the derivative of tangent of u. We talked about that in class today. Secant squared u. And the derivative of u, so u prime, is actually going to be what? The quotient rule, right? Because it's a fraction. It's a fraction, so we can use the quotient rule. So that's going to be the derivative of the top. I'm sorry, let me put this. The derivative of the top times the bottom minus the derivative of the bottom times the top, all over x plus 1 squared. Okay, and if we simplify this, then u prime equals, well, the derivative of x is just 1, so that's just going to be, that's just going to be x plus 1 minus, and make sure you put parentheses or brackets. Sometimes it's needed, sometimes it's not, but you can always, it's better safe than sorry. Minus the derivative of x plus 1, which is just 1 times x, so it's just x, all over x plus 1 squared. So the x's go away, and we have u prime equals, what, 1 over x plus 1 squared. Okay, so this is actually a pretty nice method to use if, like I said, you have something that you have to do, like other properties and other derivative rules in the function. And so it's good to sort of organize what you're doing. And let me see if we can fit our final answer over here. So f of u prime, and of course this is because we have the chain rule, it's f prime of u times u prime. All right, and so in our case, f prime of u is secant squared u times u prime, which is 1 over x plus 1 all squared. And then our final answer, because we have to replace that u with an x, secant squared x over x plus 1 times 1 over x plus 1 squared. So this is a nice method, and I mean, you might think it's more steps because you have to break up your functions, but it really helps you organize your derivatives. So if you want to use this method, and I think for some of the problems on the homework, they use this method. So I just wanted to make sure you know this. Okay, I think we just have a couple more things to do, so I actually think this will be the only video, and then I really want you to focus on your homework. All right, so we talked about one of the special cases for the chain rule, which was the generalized power rule. So we did that in class, so you have that in your notes. I wanted to now mention the exponential property. Recall that the derivative of e to the x. So the derivative of e to the x, so e to the x prime is just what? E to the x. So it's nice, pretty derivative. And in fact, like I said before, we're actually using the chain rule almost in every property, because if you think about it, the derivative of e to the x is e to the x times the derivative of x, but the derivative of x is just 1. So that's what I was talking about in class, how we sort of use the chain rule, but because it's sort of trivial, the derivative is just 1, we don't see it as the chain rule, okay? Or we don't just talk about it in terms of the chain rule, but it's really the chain rule, okay? So this example, so the generalized chain rule for, well, the special case for the exponential function is that the derivative of e to the g of x, so e to some function, equals g prime of x times e to the g of x, okay? And so let's look at this example. All right, it's not too bad. You guys had some challenging problems in class today, so these should be a piece of cake. All right, so y equals e to the cosine t. I wanted to switch up the variable because that doesn't really matter as long as you know what you're taking your derivative with respect to. So now we're taking it with respect to t. All right, so this is e to the cosine, the derivative with respect to t of e to the cosine t. Well, according to this formula, is g prime of x, so the derivative of cosine, or actually, you know what, I don't want to, I'm just going to put an equal sign here, because sometimes it's just easier to see. It's e to the g of x times g prime of x, okay? You might when you rewrite it and simplify your answer, it might have the derivative up front, but I just want you to guys, I think it's better to sort of remember it like this, okay? So it's e to the cosine t times the derivative of cosine t. Well, we know the derivative of cosine t is negative sine t, so this is e to the cosine t times negative sine t. And so this is negative e to the cosine t times sine t. Okay. Or you could have put negative sine t times e to the cosine t. That might look a little better. Let's go back. We want it to look pretty. Okay. Negative sine t times e to the cosine t. That looks all right. Okay. All right. Okay, so we're actually done. What I want you to do is go back into section 3.7, and there's a strong possibility that I might use one of the examples on the exam. I usually never do that, but if you're listening to this video, then maybe this is a heads up for you. Okay, so I want you to do that. Go back over, read all the examples, make sure you understand how they got their answers, not just look at their answers, but make sure you understand that. And you can, for now, there's a section in there that talks about the shifting and scaling rule. You can just sort of forget about that. It's the same thing we've been doing. It's sort of this, they make it a theorem in a special case, but it's really, once you get the general idea and once you understand the general rule for chain rule, you have it, so you're good, okay? So you can kind of omit that section, but read all the other examples in 3.7 and do not wait till the last minute to start your homework, all right? I will see you all in class on Wednesday. Bye.